We will start within 2 minutes. So today we will begin with the next unit, last unit of section 2, that is end block. Okay, design of end block. End block. So what is end block now? So end block is the end portion of the beam where the concentration of the stresses are maximum. That is why we need to design this block separately. Okay, so the length of the what is the length of the block and how to design that block, that we will see in this unit. Okay, so in short, if I want to tell you what is end block, now suppose this is the beam. Suppose this is the beam. Okay, and this is the cross section of the beam. The cross section of the beam. This dimension, suppose the length of the beam is L. This is the total length of the beam, L. Okay. Then here it is the width of the beam. And this is depth of the beam. So if I give naming, so this is L, this is B width, and this is suppose depth is D. Okay. Then the portion of the beam from equal to the depth of the beam. Okay, from this end, if I take a distance D, okay, and from this end also, if I take the distance D, then whatever the portion is there in that length, suppose this depth is D. So if I count over the length, depth D. So this portion, whatever this portion is there, this portion is called as the end block. This is called as end block. Okay, is it clear? So whatever the depth of the beam, suppose now B and D are the cross-sectional dimensions of the beam, then D is the depth of the beam and L is the length of the beam. If the D is 300 mm, if D is 500 mm, so from this point if we measure 500 mm, that is the length of our end block. That is end block portion that we need to design separately. Okay, because the concentration of the forces at the end block is high. Okay, so this portion is called as the end block. I hope now you are clear with the thing. What is end block exactly? Okay, so now we will start. First, we will take down the syllabus. Okay, the first is the syllabus. Here, analysis and design of end block. Analysis and design of end block. Okay, then title of chapter. So in this, I will write the highest design Indian Standard Design. IS means Indian Standard. The IS design procedure, Indian Standard Design procedure, as per IS 1343 for design design of end block is discussed in detail in this unit Okay. So this is the about title. Then importance of chapter. Importance of chapter. So this chapter deals with deals with design procedure and standard design as per IS code consideration as per IS code consideration. Okay, full stop. This is very important. This is very important chapter from design point of view. Design point of view for end blocks. Okay, this is the importance of the chapter what we have seen right now. Now, central idea of the chapter. Next is the central idea of chapter. What is the idea behind this chapter? So, the end block is the end portion of the pre-stressed concrete beams. The chapter mainly focus on design of end block and evaluation of horizontal and vertical bursting forces developed on the end block. And now finally we'll see the chapter outcomes. Okay. So After successful completion of this chapter, students will be able to first analyze the end block, analyze the end block for bursting forces. Second, design the end block. Students will be able to design the end block. Okay, so these are the chapter outcomes of this unit. So I have told you in short what is the end block. The end portion of the beam, the length of that portion is equal to depth of the beam. That much portion, that portion is called as the end block. So somewhat theory is also there in this unit. We will see that theory side by side. Okay, I will write it down the theory. You also copy it down, and at that time I will explain you what does it exactly mean, and then we will move forward, and then we will solve the numericals based on this. Okay, so now first is the end block. I will tell you the definition of this end block. End block. So end block is nothing but the portion of the pre-stressed concrete beam near anchorage of tendon, near anchorage of the tendon is known as end block. Okay, so end block is nothing but the portion of the pre-stressed concrete beam. It is the portion of the beam only. Okay, it is not a separate portion. It is the portion of the beam only, which is nearer to the anchorage of the tendon. Okay, and the length of which is equal to the depth of the beam. So next line is the length of end block. The length of end block is usually taken as depth of the beam. Is usually taken as depth of the beam. Okay, so this is very simple thing. Just it is said that it is the end portion of the pre-stressed concrete beam nearer to the anchorage of the tendons. Okay, and the length of that is equal to the depth of the beam. So I will draw one diagram then, so that it will be clear to you how exactly the stresses behave. Suppose now this is the cross section of the beam. So this is the width B. This is the overall depth D. Okay. This is the width B. This is the depth D. Now, if I draw the length of the beam over here, this is the length. Okay, I will draw only for the end block. This is the length. I'm not drawing total beam. This beam is continued. I'm drawing only the portion of end block. So this distance, whatever the depth of the beam, same is the distance we are taking for the end block. This is our end block, D. Okay, whatever the depth of the beam, same distance I have taken over here. Now anchor plate is there. See, whenever we apply the force, see, now this is the beam. Suppose now this is the beam. Okay, this is the beam. Now I can apply the pre-stressing force directly on this cross section. I can apply the pre-stressing force directly on this cross section. Then also, if I want to calculate the stress, then it is load divided by this cross sectional area. This we can easily calculate. But in the case of pre-stressing beams, to transfer the load evenly, to transfer the pre-stressing force evenly, what we do, we connect here one anchor plate. One plate is connected over here, not on the entire depth, up to some depth. Okay, the plate, so where I have placed my two fingers, these two fingers. Suppose now in this portion a plate is connected. This plate is known as the anchor plate. It is having some dimensions. The width of the anchor plate is nearly is equal to the width of the beam, but depth of the anchor plate is different from the depth of the anchor plate is different from the depth of the beam. Okay, so if I draw that anchor plate over here, why that anchor plate is included? To transfer the load evenly. Okay, so I can show you here also the anchor plate. It is like this. This is the anchor plate. Along the length, you can see it like this. Now, if I draw the same anchor plate over here, so it is nearly comes here at this portion, at here. So this is nothing but this is my anchor plate. Okay. So this portion is the anchor plate. For your understanding, I am hatching this. Okay. So this is nothing but the anchor plate. This plate is called as the anchor plate. I will give the name to this also. This is anchor plate. Now see, when you apply the pre-stressing force P, when the pre-stressing force is applied, okay, so here the pre-stressing force is applied. P is the pre-stressing force. Okay. Now, how there is a due to this pre-stressing force, there is a compressive stresses are getting generated in the in this end block. Okay, and those compressive stresses are having very high concentration near the support. And as far as then once we start moving from away from the support, then that concentration is goes on reducing, and after some level it is uniform. After some level it will become uniform. Okay, so if I show the diagram here, in the diagram if I show that, then this will be like this. First I will draw the neutral axis. So this is the neutral axis of the beam. Okay. The neutral axis. Now here I can show it to you. So the stress concentration will be like this. Here the concentration is maximum, and then it will move like this. Okay. At bottom also, this is the stress concentration. This is the concentration pattern which is observed by the experimentation. Okay. So in this way, the concentration will be there, stress concentration. Then it will start spreading. Okay, like this. Okay, you draw the diagram with accuracy. This is the compressive stress concentration due to which the bursting forces are getting developed in the beam. Okay, due to which the bursting forces are getting developed. Okay, so this is the diagram. So this is the pressure lines. These are also called as the pressure lines. These are also called as the pressure lines. Okay. Pressure line. So in this way, the compressive stress is acting. Are you getting the thing? In this way, the compressive stress is acting. This is the only end portion of the beam. I am not considered the total entire beam. Okay. What is meant by bursting forces? Bursting forces means due to the pre-stressing force. See what happens actually. Due to this pre-stressing force, here is the anchor plate. So this pre-stressing force is transferred to the tendons and the surrounded concrete with the help of this anchor plate. And due to which there is a high concentration of the compressive stresses are getting developed. Okay, high generation of compressive stresses. So it will try to compress like this. It will try to compress like this. And if we don't design our beam properly, then there will be the what we can say splitting of the tension reinforcement. There will be the chance of splitting of the tension reinforcement. Right? निघून पटकन बाहेर उडते तिथे reinforcement. Okay, whatever the place you have allocated for the reinforcement, it will not fit into that place because of this high compressive stresses. Okay, and this high compressive, due to this high compressive stresses, there will be the splitting of tendons, and that splitting of tendons is happening due to the forces. That forces are called as the bursting forces. So due to the compressive stresses, the bursting forces are getting arise, and these bursting forces are causes the splitting of tendons. Okay, the tendons are getting dislocated from their places. So the force, the name of that force, see here the compressive stresses are there. So instead of calling as a compressive force, the name is given as bursting force. Why it is called as a bursting force? Because due to that force, the reinforcement which is placed at, you have allocated the definite location for the reinforcement in the beam. So that reinforcement is getting dislocated. Okay. So that is why it is called as the bursting force, and it is happens suddenly. It is happens suddenly, like a busting, like bust. Okay. So आपण म्हणत नाही का bomb blast, तसं blast. Okay, so that is why the force which causes this, it is called as the bursting force, and it is getting developed because of compressive stresses, high concentrated compressive stresses, and these compressive stresses are getting developed because of pre-stress. कळतंय? म्हणजे आपण प्रिस्ट्रेस करायला जातो, प्रिस्ट्रेस केल्यामुळे कंप्रेसिव्ह स्ट्रेसेस डेव्हलप होते, आणि कंप्रेसिव्ह स्ट्रेसेसमुळे बस्टिंग फोर्स डेव्हलप होतो, आणि हा बस्टिंग फोर्स काय करतो, तर इट विल ट्राय टू डिसलोकेट युअर रिइन्फोर्समेंट. Okay, is it clear?
Yes, sir.
Okay, so this is the actual theory of this end block. So now we have to design this end block in a such a way that, or we have to analyze the end block, we have to calculate all these forces which are acting on the end block in a such a way that our design should sustain all these forces. It should be able to absorb all these forces, and it should not fail. Okay, so there are two types of bursting forces which are acting and which we are going to calculate. One is called as horizontal bursting force, second is called as vertical bursting force. Okay, because the stress is the quantity which is spread all over entire area of the end block. So due to that, it causes the horizontal bursting forces as well as vertical bursting forces. So this is all about the compressive stresses. Okay, now if I show you the, what we can say, the line of action of tensile stresses, how the tensile stresses are getting developed over here. So the tensile stresses will be like this, the concentration of the tensile stresses will be like this. Okay, in this way the tensile stresses are getting developed. Okay, this is the tensile stresses. Okay. So this is the red dotted line shows you the how the tensile stresses are acting. Okay, and the blue line shows you how the concentration of compressive stresses are there, how the compressive stresses are acting. Okay, and due to these stresses there is a generation of the forces, and those forces we call them as a bursting forces. Okay, and those bursting forces, if we don't take care of those bursting forces while analyzing and designing, then those bursting forces will try to dislocate our reinforcement which is provided in the beam. And once the reinforcement is getting dislocated, that is the tendons are getting dislocated, then there will be the failure of the beam. There are huge chances of failure of the beam. 99% the structure will get collapse. Okay. So further in this regard, further theory says that now we will take some considerations. Consider a beam. Consider a beam of width B. Of width B. I have already drawn the cross section. You can refer the diagram of width B and depth D. Okay. So this is the cross section BD. Let the pre-stressing force be P applied at bearing area B D dash. Okay, so this dimension they have considered this as a D dash. This whatever this length is there, anchor plate depth is there. This it is D dash. Okay, and width is B. So B D dash. On this anchor plate, we are applying the pre-stressing force. Okay. So what is the area? It is B is the width, D dash is the depth. B D dash on the end face of beam as shown in figure. Okay, as shown in figure. Now, if I ask you, this pre-stressing force is acting on this area. Okay, on this area. So, eventually from anchor plate, it is getting distributed over this entire face of the beam. Okay, entire cross section of the beam, this entire cross section. So you know the width of the beam is B. Here the width of the beam, depth of the beam is D. Okay, and this is the pre-stress. So if I ask you the stress, what is the stress getting generated? Then stress is equal to, you can tell me, it is load upon area, basic formula. So P by BD. Okay, load upon area. Area of cross section is B into D. Eventually from anchor plate it is going to transfer over the entire what we can say face of the beam. Okay, so you can tell me it is the stress is nothing but it is P load upon area, so P divided by PD it is. Okay, but actually it is observed experimentally that although this formula true, P by BD should be the stress, but actually practically we observed that here the concentration is greater than this quantity. Are you getting my point? Here you will evaluate that. What is the stress? Stress you can calculate it. It is P by A. Some quantity you will get 100 Newton per mm square, 200, 300. But when the research is done on this, then it is observed that here the concentration of the stress is greater than P upon BD. Okay, so stress is greater than that. Okay, and that greater quantity will remain as it is up to this point, and after this the stress concentration is normal, which we can calculate by our formula P upon BD. Okay, so suppose now if I tell you, I consider one section over here. So suppose this is my section line here. Okay, suppose this is my section 1-1. I call this my section, it is as 1-1. Okay, so the part of the beam from the end block to the section 1-1 is called as the end block. Okay, section 1-1 पासून जो काय पार्टचा beam आहे, that part is called as the end block. The stress concentration in this area is greater than P by BD. Remember this point. That is why we are designing these blocks separately. आता गरज काय आपल्याला? We have already studied how to design the pre-stressed concrete beams. We have seen the steps for the design of rectangular pre-stressed concrete beam, for the design of I-section concrete beam yesterday only. So you can use those steps for the design. Okay, but here the main thing is that the concentration of the stress is greater. Okay, so I can write further in this regard that stress here at the section at the section close to end phase, okay, the stress is greater, far more greater than P by BD. Stress is greater than P by BD. Okay, and the stress, with this I have already explained to you right now. The stress beyond section 1-1, the stress beyond section 1-1 is P by BD. Then this formula holds good, P by BD. After passing that section 1-1, whatever we have shown over here, this section 1-1. So in the end block portion, the stress is far more greater than P upon A. So normally you calculate the stress P by A, but it is greater. Once that stress pass this line, pass this section 1-1, then it is our usual stress, that is P by BD. By using that, we can easily calculate that. Okay. So the part of beam, from end face to the section 1-1 is called as end block. Okay, this is called as end block. Okay, so this is the introduction of the end block. I hope now it is clear to you. What is the end block exactly? Is it clear now? What is the end block? So here there are various methods of designing this end block. Okay, and some fixed formulas are also there to design this end block. So this is very chapter is also very easy. There are two types of numericals which are asked on this unit. One is the design of end block by Guyon's method, and second is the design of end block by Magnus method. So only two types of problems are there in this unit. There is no variety. Okay. So if you observe in the second section, there is only variety in the cable profile. The unit cable profile is there. In that, many variety of the problems are there, which we have covered almost. We have taken 8 to 10 lectures on that. Okay, many of the problems we have taken on that. But here there is no variety. Only there is a changes in the values. Same numerical you will get in the examination. Only there will be the change in the value. Okay. So different scientists have worked on this. And they have found out the different methods to design this end block. So out of which in this unit we are going to study the Magnus method and Guyon's method for the designing of the end block, which is frequently asked in the examination. Okay. So first we will move to the next point. Magnus method. First is this Magnus method. So here I will write, in this method, the stresses due to anchorage bearing are taken to be dispersed over a length of beam equal to depth of beam. So same theory is here. Just what is the difference? See, if you see this diagram, this is the dispersion of the stress. This is nothing but this is the dispersion of the stress. Okay. So we have shown the dispersion of the stress in a non-linear way. But the Magnus, what does he says? He says that the stress is getting dispersed in this area, in this end block. The angle of dispersion is 45 degree. Okay, the angle of dispersion taken. So for dispersion, if I show the line, it will be like this. This will be the line for the dispersion, and this angle is 45 degree. Okay, and after where this dispersion line intersect this beam, okay, so from that point you have to consider whole depth of the beam for the calculation. Okay, that we will see in the numerical, that is called as dv. Okay, depth of the beam, so that we will see later on. So the dispersion is same, but Magnel says that dispersion is in the 45 degree angle. So if I show you the different forces over here, then I will draw the diagram first. So here, this is the beam. Okay. And this is the length of the beam, which is equal to depth. So D. I will write here D. Then tendons are also placed over here. So I will show the tendons like this. Where it is placed. This is the thickness of the tendon. Okay, this is the tendon which is placed. This is the rod which is having some diameter. Then we can see the plate. Here may be the anchor plate where we apply the stressing force. Okay. And the bearing plate, this plate is the bearing plate. Here in the central portion, if I consider this central portion, then here the stress in this direction will be there, vertical direction. This is called as Fz. This is called as Fz, vertical direction stress. Then there will be the horizontal direction, the same stress will be there. This is called as Fx. This is called as Fx. And then here the shear stresses are also getting developed. Okay, so the shear stress I will show. This is the shear stress. Okay, now how to show the shear stresses, that you also studied in geotech also. This is there. So this is the shear stress Q. Okay, shear stress Q. So these types of stresses are acting on this end block portion. This is said by this who? Magnus. Okay, Magnus has given this theory in front of us, that horizontal stresses, that is Fx, vertical stresses, that is Fz, and shear stresses, that is Q. This is acting on an element in the end zone. This is this is one element we have considered. Elementary strip, you can say. The rectangular elementary strip we have considered. If we take out that rectangular elementary strip separately from this end block, and if I try to analyze this, then the Magnel says that on that elementary strip, the horizontal stresses are acting, as well as vertical stresses are acting, as well as shear stresses are acting. So we have to evaluate all these stresses to analyze, to know the value of the stresses acting on the end block. See, in the design subjects, okay, it may be design of concrete structures, or it may be design of steel structure. What is the difficult part? Analysis is difficult part, or design is difficult part? So remember that design is never difficult. Design is always easy. For the design, there are certain steps. You have to follow that step, and you will automatically get the design. Okay, just you need to take some checks. If those checks are satisfied, your design is okay. Okay, in the design, you are having choice. You can go for either depth 100 mm, 120 mm, 150 mm, whatever you want, you can do. But the design is totally depend upon the analysis, and the analysis should be perfect. Okay, so analysis is the most difficult part. Analysis must be precise. If you go wrong in the analysis, eventually your design will be wrong. Okay. So what Magnel says that he has analyzed this one part, that one strip, one rectangular strip in the beam. हे बीमचा पोर्शन आहे बरं का सगळा, हे एंड ब्लॉक आहे. इथं मी परत एकदा ड्रॉ करून तुम्हाला दाखवतो. दिस इज अवर सेक्शन 1-1 which I have previously drawn. Okay, here that section 1-1 is still there. Okay, this is our end block only. I am just talking about end block only, nothing else. End block. I am not talking about entire beam. Remember this. So Magnus, what he did, he has taken one strip from this entire beam, end block. From this end block, he has taken one piece there, and he has analyzed that, and he told us that on this elementary strip, the vertical stresses are acting, horizontal stresses are acting, and shear stresses are also acting. Okay. Now we will see how to find out these stresses. This is nothing but Magnus method. Once you evaluate these stresses, you can provide the design. Once you know the stress, you can calculate the force. Once you know the force, you can calculate the moment. Once you know the moment, you can provide the steel. So rest of the procedure of designing is the mechanical procedure. There is no brain required for the design. The brain is required for the analysis only. Okay. So now see further what he says. Further consider an elemental unit situated within end zone. This I have already told you. One elementary strip we have considered. The elemental unit is subjected to three stresses. Okay, three stresses subjected to three stresses: Fx, Fz, and Q. Fx, Fz, and Q. Where Fx is equal to what? Fx is equal to horizontal stresses. Fx is equal to horizontal stresses. Fz is equal to vertical stresses, and Q is equal to shear stress. Q is equal to shear stress. Now we will see how this horizontal, what is the formula for the horizontal stress, and how that horizontal stress is calculated. Okay. So now horizontal stress. That is Fx. समझते ना काय चाललंय ते? First we have seen what is exactly end block is. पहिल्यांदा तुम्हाला मी काय सांगितलं, what is exactly the end block is, how the pre-stressing force causes compressive stresses, what is the behavior of compressive stresses, and due to compressive stresses how the bursting forces are arises, and those bursting forces are nothing but the horizontal and vertical stresses. So in the Guyon's method it is called as the bursting forces, horizontal bursting force and vertical bursting force. In the Magnel's method he called them as the horizontal stresses and vertical stresses, and this causes to dislocate the reinforcement. That is why we are analyzing this and designing this. In analyzing now, we are studying the first method, that is Magnel's method. So in the Magnel's method, what Magnus had did, Magnus had taken out the one portion of the elemental unit or elemental strip from the end block, and he told us that by doing research on that, he told us that on this elemental block, three stresses are acting. First is the horizontal stress, Fx. Second is the vertical stress, Fz, and third is the shear stress. Okay, so up till now, within last half an hour, we have studied these points. Okay, so now in that Magnus method, now we are going to see what is the formula for the horizontal stress, how that formula comes. Okay, so now I will write further horizontal stress Fx. So this is the summary I have told you what we have studied. So now it is assumed that It is assumed that the compressive force P from the anchorage will disperse at an angle of 45 degrees. This I have already told you. What Magnel assumes, Magnel says that the compressive stress is dispersed at an angle of 45 degrees. Okay. Now I will draw the diagram regarding to this. The diagram, it is better if you draw this diagram. Okay. So now this is the diagram. Here our section line is there. Okay. This is the end block portion. This is our section 1-1 as it is. Up to the section 1-1 our end block is there. Remember this. So this is 1-1 which is as it is. Okay. And this is D. This length is nothing but depth of the beam because this is end block. So this is D. Now I will draw here the tendon line. Okay, so first before drawing the tendon line, okay, now you imagine the neutral axis is also there at this point center. Okay, so this is the tendon line. This is the diameter of the tendon which we are seeing. त्याची thickness असणार ना बारची काहीतरी. So that I have drawn over here. This is the tendon line. Now I will draw this anchor plate. So this is our anchor plate. Okay, it is not perfectly drawn by me, but you can draw it correctly. Now see here I will show the compressive stress line. What Magnel says. This line, suppose I draw here one horizontal line. If I draw here the horizontal line like this, okay, and here also from this bearing plate, because at this point we are applying the force, no pre-stressing force on this bearing we are applying. So we are considering the dispersion from this end only. So here the dispersion will be like this. Okay, it will be like this. So this is the dispersion of the compressive stresses, and this angle according to Magnel is 45 degrees. Okay. This angle is 45 degrees. Okay. Are you getting my point? So in this way, he has told that there is a dispersion will be there. So this diagram, I will draw quite big diagram so that you will understand dispersion. It is actually at the angle of 45 degree, but now we have to draw much more things in this diagram. So I will draw it like this. Okay, suppose that this angle is 45 degree up to this point. This angle is 45 degree, and here it is 45. It should not be the case that both are coming or one below each other, because this anchor plate, this tendon, it is sometimes it is concentric, but sometimes it is eccentric. Okay, so it is not exactly the case that every time it will come below that. Okay, it depends upon the position of the bearing plate where it is placed. So this is M and N. These are the points of bearing plates. Okay. So now if I drop this line below, if I draw a straight line from here, draw a perpendicular, then I will get one point below. Suppose that this point I will call it as C, and this point is D. Similarly, where this line intersects over here at this point, this is suppose A, and if I project this upward, if I project this line perpendicular, if I drop one perpendicular from here, then this is the point. This is the point. Okay, so I hope now up to this point it is clear. So further, I will write the things also and I will explain it, so that partly I will drawing the diagram. So I am drawing the diagram so that you will able to catch it. So what we have done, we have shown the dispersion. Okay, dispersion, that is ND and MA dispersion. From D we have dropped one perpendicular up to the and it will intersect at point C. From A also one perpendicular, it will intersect at point B. Okay, so further if I write, let the lines of dispersion, the lines of dispersion meet the upper and lower faces, at D and A as shown in figure. Okay, as shown in figure. The centroid of stress zones, the centroid of stress zones are located. So these are the stress zones. These are the different stress zones we can say, and the centroids of these stress zones are located from NM to EF. So I will consider one more section over here. Okay, one more section will be here, and this will be, suppose we will consider it randomly. It is EF. Okay, I will consider one more section over here like this before, and suppose now this is point E, this is F. So what they have mentioned over here in this sentence, the centroid of stress zones are located from NM to EF. So this is NM and this is EF. So the centroid, what is the centroid of NM? It is located. What is the centroid of BA? It is located. What is the centroid of this DC? It is located. And what is the centroid of DF? It is also located. Okay. So if I locate that centroid over here right now, if I show you where this centroid is, then suppose now O1 at this point here, O1 is the centroid of this NM. It will be at the center now, it is rectangle. So O1 is the centroid of this NM. Okay. Then O2, suppose this O2 is the centroid of this BA. Then you can see that the centroid will getting shifted. So here O3 will be the centroid, which is over here. This is getting shifted due to this dispersion. Okay. And then O4 may be the centroid of this EF, which may be here. And if I draw this centroidal line, then this centroidal line will also behave in the same manner like the dispersion of the compressive stresses. So this is the centroidal line. Okay. This is the centroidal line. So this is the centroid. This is the centroid. And this is nothing but tendon. is nothing but tendon or cable. Okay. So for the section XX, now for the section XX, now I will consider one more section over here. Okay, after O2, and that is section XX. So that section I will draw it. So this is section XX. This is the section XX. Okay. Let the section intersect this dispersion line at this point, and let this point be S. Let this point be S. And at this S point now we want to calculate this horizontal stress effects. Okay, if we want to calculate this horizontal stress effects, then what will be the depth of the section? The depth of the section which is need to be considered is, so which color should I use? All colors. So this distance is nothing but the depth of the section from the point. Okay, from this point over here. So this is called as dV, depth of the section. Okay, dV. It is not the entire depth which is considered, because the point S is not at the topmost edge where the X point is there. So here for the section XX, the stress the stress at any point, the stress at any point at a distance y from centroidal line is given by now the formula is there. See, for any general section XX, this is the any general section XX, the stress at any point, so here we have considered point S, the stress at any point on this section, okay, at a distance y from centroidal line. So this is the centroidal line. So from the centroidal line at a distance y, so this distance is y, or where you have taken the point. Suppose I have taken point S is here, you can take the point over here also, at this point also, anywhere. So at a general distance y, whatever may be the y distance, this it is given by, okay. So this stress is finally, it is given by the formula. The formula for this is Fx is equal to its formula we can see over here. Fx is equal to P upon T is the stressing force upon BD, but here depth you need to consider the dV, whatever may be the depth below that point. Okay, whatever may be the depth below that point, that you should consider dV, plus if it is eccentric, then it is P EVY by IV. So eccentricity at that point from the neutral axis, then IV is the moment of inertia, Y is the distance. Okay, so where dV is, I will tell you the meaning of each term. dV is depth of the stressed zone. So in our case it is XS. See, if you see the diagram, XS means this. Okay. So this is the stress zone. On this point we want to evaluate the stresses at this point. So whatever the depth is, this depth is dV. From this point up to this point, total this depth is d. Okay, depth of the beam is d and length is also d, because whatever the depth of the beam, that portion we have taken for the end block. Now in this end block we have taken one point where we want to evaluate this horizontal stress. So the distance of this point from this point to up to the depth, this total depth is not equal to this total d, but because this distance is d. So this is dv. This is called as dv. Wait, the notation is given dv. Then iv. iv is the moment of inertia, that is mi, of the stressed section. That is, it will be same BD cube by 12 if rectangular section is there. If I section, T section is there, then you have to calculate that. Okay. So mi of stressed section. Then EV is the cable eccentricity. Cable eccentricity at stressed section. At stressed section. From centroid, we can measure the eccentricity. So here, if you can see, this is the centroidal line. It is going at this point. We are considering this is the centroidal line. So whatever may be, this is the centroidal line. Here we are taking on this axis. Our point is there. This is centroidal line. So from this centroidal line, whatever may be the eccentricity, that eccentricity we need to consider. Okay. So this is the eccentricity of the cable. EV, IV. Here DV is used notation. That is why here EV आणि IV असं notation दिलेलं आहे. तुम्हाला हे नको असलं V तर you can remove it. You can remember PE into Y by I. Okay. So this is the formula. Calculate the effects. This is the formula to calculate the effects. If eccentricity is 0, then this term will become 0 and you can get it as P upon BdV. This is to calculate the effects. Effects is the horizontal stress. Okay. Now for shear stress Q, for shear stress Q. Okay. Now direct formula is there for this. Okay. The shear stress distribution at any horizontal plane is given by Q is equal to KQ into S upon BD. Okay, KQ into S upon BD, where KQ is the shear stress factor. Okay, where KQ is the shear stress factor. This value is already many of the times it is given in the problem. Shear stress factor. This value you will get from IS 1343, which is used for the design of stress concrete members. And S is equal to part of pre-stressing force at section 11 acting above at section 11. Okay, so how to calculate this as what is KQ, that we will see while solving the numericals. Right now I am telling you just formulas. This formula we need to use. This is for the shear stress. Okay. And this is Magnel's method we are seeing. And third, vertical stresses. So vertical stress distribution at any horizontal plane is given by Fz is equal to Kz into M upon Bd square. Okay, so it is Fz is equal to Kz into M upon Bd square, where Kz is equal to vertical stress factor, okay. Then M is equal to moment due to force S. We have already seen. This is S. Okay, S part of stressing force at section 1-1. So moment due to force S. Okay, that moment it can be calculated as it is at any general section Sx, that is Sx into any distance y0. एक जनरल फॉर्म्युला लिहिला आपण F into D लिहितो ना, moment is M is equal to F into D. F is the force and D is the lever arm. Similarly, a general formula it is written S is at any point X, the force is Sx and the distance of this Sx from the centroid is y0. So the moment is Sx into y0. In general, a terminology is written. Okay. So here that y0 is equal to the distance of line from action of S to the centroid. Okay. So here what is happening, we have seen the formulas for all the three things. First is this horizontal stress. Okay, this is the formula for horizontal stress. Then we have seen the formula for shear stress. For horizontal stress formula it is P upon VdV plus PEVy upon IV. This is the formula for horizontal stresses. For shear stresses, Q is equal to KQ into S upon BD. Then for vertical stresses, the formula is Fz is equal to Kz into M upon BD square. This is the formula. So due to this, further what he says that, Magnel says that, due to this concentration of the vertical and horizontal stresses and this shear stress, what is happening? The principal stresses are getting generated. Okay, the principal stresses are getting generated, and that principal stress we can calculate those principal stress by using the formula. So the principal stress sigma, it can be calculated as Fx plus Fz divided by 2. This formula also you have seen already, plus minus under root in sum in the chapter principal stresses and planes. Okay, that this formula was there, sigma x plus sigma y by 2 plus minus under root sigma x minus sigma y by 2 square plus q square. Same formula is here, fx plus fz, just the notations are different. Sigma x was the horizontal stress and sigma y is the vertical stress while we studying that chapter in the song. Here just the notation is different. Fx is the horizontal stress, fz is the vertical stress that we have considered. So fx plus fz by 2 plus minus under root, it is fx minus fz by 2 bracket square plus q square, shear stress square, plus q square. Okay, this is the principal stresses, major and minor principal stresses. Plus and minus sign is there, so you can easily evaluate major and minor principal stresses. Okay, so at the top the major principal stress is there, which is generally compressive. At bottom minor principal stress is there, which is tensile, okay, which is tensile in nature. So after this, the position of the principal plane. So position of the principal plane, that also we can find out. Position of principal plane, position of, here PLE should be there, huh? PAL is different. Position of principal plane, it can be calculated as, this position is tan of 2 theta is equal to 2q divided by fx minus fz. Okay, fx minus f. In this way, we are going to calculate the principal stresses also. Here you can see plus sign is at top, minus sign is at bottom. So at top, compressive principal stress is there. At bottom, tensile principal stress is there. Okay, so at top it is compressive, at bottom it is tensile. That is the meaning of this. And tan of 2 theta, this is the formula. From this you can calculate the value of theta also, and you will get the position of the principal plane. Okay, and from this you will get the position of the principal plane. So now after this we will see the all the formulas. Okay, you can see all the formulas. See the formulas one more time, and then we will start with the numerical. Okay, you can see these formulas. I will give you half a minute. See the formula once again. If you have noted down, if you have taken the screenshot, and then we will take the numerical. Okay. So Fx, Q, then vertical stress Fz, and the principal stress, major and minor principal stress. Major is at top, minor is at bottom. Okay. And the position of the plane. So these are the formulas. Now we will move for the numerical. So pre-stressed concrete beam, stress concrete beam, 400 mm wide and 800 mm deep. The stress concrete beam is, here is missing, is 400 mm wide and 800 mm deep. Full stop. Okay. Determine the horizontal comma vertical and shear stresses shear stresses at a distance 400 mm from from the end of from the end of horizontal section horizontal section. Okay, so we need to calculate these stresses. Okay, so where at a distance of 400 mm. Okay, so at a distance of 400 mm we need to calculate. So total length of our end block is 800 mm, because the depth of the beam it is given 800 mm. So what is the total length of our end block? It is 800 mm. But we do not need to calculate it at 800 mm. They have given us the point which is at a distance of 400 mm. Okay, so at that point we need to calculate the horizontal, vertical, and shear stresses. Further, they told us horizontal section. So here the sentence is not complete yet, comma. Shear stress at a distance of 400 mm at the end of horizontal section. First, कुठला horizontal section तर through center. This through the center, to the center. Okay. And second, at the level of the edge of anchor plate. तर अँकर प्लेटच्या कडेचा एक पॉइंट दिलेला आहे कडेवरती आणि दुसरा कुठला प्लेन आहे थ्रू द सेंटर. या दोन्हीला आपल्याला कॅल्क्युलेट करायचं. ओके, further it is continued. Note that the anchor plate is 300 mm wide, and 200 mm deep. Full stop. The pre-stressing force is 1000 kilonewton. Find also the principal tensile stresses at the above section. Full stop. Take Kz is equal to -5 and Kq is equal to 1.25. Full stop. Refer the figure below. The diagram is also given to you. This is the numerical. So now I will draw the diagram. Then we will read the problem and we will see the diagram once again. So here the diagram is end block portion is there. This is the end block portion. Here the anchor plate is connected. Okay, the anchor plate is there. Now the dimensions, they are given it like this. So here at this point, one marking is there. Then here it is 200 and 200. This is also like this. Okay, so they have given the distances like this. From here to here it is 200. Again from this point to this point it is also 200. Again from this point to here it is also 200. Again at the bottom, this point to this point, last point, it is also 200. So these distances are 200 mm, 200 mm, 200 mm, and 200 mm. So total depth is 800. Total depth they have given us 800. Now what they have told us in the problem, they have told us that the shear stress where we need to calculate at a distance of 400 mm. Okay, so from this point I will measure a distance of 400 mm. Okay, suppose the distance is here at this point. This is 400 mm, and at this point now I will take one section. Okay, so this is my section line now. At this point I have taken one section. So here I need to evaluate the forces. Okay, here I need to evaluate. This is already given in the problem. Whatever I am drawing, this is the given diagram to you. The diagram is अशी दिलेली आहे तुम्हाला देताना. Okay. Then they have also shown here the centroidal line with this dotted line. This is the centroidal line. And here at the center point we need to consider, this is our second point, through the center. Okay, through the center means the points which are at the center. So let it be this point is Q. Okay, through the center point is Q. So this is the plane QQ. Here also if we consider Q. And then second point, what they have told us, at the level of edge of anchor plate. At the level of edge of anchor plate means what? Edge of anchor plate, this is the edge of anchor plate. This is the edge of anchor plate. So here, this is the point P where we need to calculate the stress here. Okay, and edge of anchor plate will be here also, which will be same. Whatever कुठल्याही point ला calculate करा, answer तुमचं तेच येणार. So edge of anchor plate. We will consider this point P and point Q where we need to evaluate the forces. Where we need to evaluate the forces. Okay. So here one more thing is there. They have placed the tendon concentrically. So eccentricity will be 0. There is no eccentricity. So this is the given problem. Okay. This is whole. It is the given problem. Also they have given dotted line, but which is not required. Here at this level they have given some dotted line like this in the figure. Here also some dotted line this. If required, then we will see. So now moving further to solve the problem. So I want to calculate what is the horizontal stress, then vertical stress and shear stress at point P and at the section horizontal section PP, and what is the shear stress, vertical stress and horizontal stress at the section QQ, at the horizontal section QQ and horizontal section PP. There I need to calculate these three stresses, which is and these planes are required located at a distance of 400 mm from the edge of the end block. Okay. So now first I will write here allow 45-degree stress dispersion from top from top and bottom edges bottom edges of the anchor plate. Okay, so it is assumed. So still we have written over a 45-degree dispersion. Then length of end block, length of end block, which is equal to depth of beam, depth of beam, which is equal to 800. Okay, 800. Then here you can see the dispersion. If I draw the dispersion, it will be like this. If I draw the 45-degree dispersion line, it may be like this. Somewhere here. Okay, it may be like this somewhere. So in between this dispersion, if the any point is there, then your depth is dB. Now what depth you are going to consider for this? Now we are going to consider the whole depth for the calculation. So now this is our whole depth, which is dV, which is equal to d. If your point is situated in between here, somewhere at this point, at this point, at this point, then the depth below that point you should consider, that is dV. Okay, from this point up to the bottom, from this point up to the bottom, from this point up to the bottom, that will be dV. If our point is located in between this dispersion line, but now at a distance of 400 mm, it is far too away. Okay, as the total depth is 800, so it is at the center. Okay, so 45-degree dispersion is the quite big angle. So it will not be there in the dispersion range. So it will be dV, that is the total depth must be d. Okay, so next is that horizontal stress, horizontal stress Fx is equal to, it is P by A, which is equal to, P is the pre-stressing force, which is given as 1000 kilonewton. P is the pre-stressing force, which is given as 1000 kilonewton. 1000 into 10 raised to 3 divided by BD. Okay, here instead of A, I will write BD. BDV. So dV is nothing but d. Okay, and here the eccentricity is 0. So that b, where the value of b is width of cross section is 400 by 800 now, beam cross section. So which is equal to, what is the answer? 3.125. Okay, it's 3.125 Newton per mm square. This is the horizontal stress. So if I show here the horizontal stress, I can draw the diagram of this horizontal stress. See, this is the baseline, or you can draw the diagram like this. So here, this is the horizontal stress. It is like this. Okay, and this horizontal stress affects its value is 3.125 Newton per mm square. 3.125 Newton per mm square. Okay. Now analysis of this section PP that we will do. Okay. After the calculation of horizontal stress, now analysis of section PP that we are going to do. So first of all, we will calculate the moment due to this stress, and then we will solve it further. Okay. So at the level, second we will consider at the level of edge of anchor plate. So in the problem, this is asked at the second point, but we are taking at first. Okay, at the level, this point, at the level of the edge of anchor plate. Okay, at the level of the edge of anchor plate means what? This section PP, which is at the end edge, that we are going to consider. Now the analysis of that. Okay, here I will write in brackets section PP. So second point we are doing earlier. Okay, so moment M. Now I will calculate the moment. So moment M is equal to, now what is the moment? Moment M is equal to, what is the moment now? Here I want moment. Here at this point. At this, about this section, I want moment. Okay. So if I draw this area separately, see, if I draw this area separately, if this is for your understanding, I am drawing. If I draw this area separately, it will be like this. Okay. So here it is, your PP section is there, PP. And you can see this length up to this point it is 200. Then up to this point it is 200. So this is the middle point of these two. This is the middle point of this 200. So this will be 100. This should be 100. This distance. Okay. From this point to here it is 100. From here to here it is also 100. Okay. It is evenly placed. So this remaining also 100. This will be 100. So if this total is 200, here you can see this total is 200, out of which this is 100, then this remaining will be also 100. And but this much is 200. So 200 plus 100. So this total is 300. This is 300 mm. And this distance is already known to you. This horizontal distance. This is how much? This is 400. So this will be 400. Okay. So now on this area, what is the stress is acting? Stress, I know it is 3.125 Newton per mm square. This is the concentration of the stress. Now what I want to find out, now I want to find out first what is the UDL which is acting on this area. What is the UDL? And I want to take the moment of that. So the value of this UDL will be how much? If the stress is 3.125, this length is 300, this length is 400, then the UDL acting over here will be 3.125 into, I want the UDL on the length of 300 mm, so I should multiply it by 400. Okay, so this will be my UDL. So this value works out to be 125 into 400. So it will be 1250 Newton per mm. Okay, 1250. And now this is the 1250 is the UDL. Now if I draw this separately again, this is again for your understanding I am drawing, not required in the exam. So again if I consider this separately over here, okay, and here this is my plane P point is there, and now this is my UDL. This is my UDL. Okay, its value is 1250 Newton per mm. Please check the calculations also. And my this span is 300 mm. Okay, this span is 300 mm. Now I want to find out the bending moment. So my bending moment will be WL square by 8, as this is simply supported. Okay, so my bending moment will be WL square by 8, where my W is this 1250 and my L is what? It is 300. Okay, 300. Not it is WL square by 8, it is taken as WL square by 2. It is supposed to be cantilever. WL square by 2. Maximum moment we will take. Okay, maximum moment will be, we are going to take. So it is taken as WL square by 2. Okay, so now Here I will do it. M is equal to, so M is equal to, in first bracket, 3.125 is my stress multiplied by 400. Then this is the UDL, whatever I am getting. This is my W into L square. L is 300. L square, it is 300 divided by 2. So this is nothing but WL square by 2. Okay. So if you solve this, you will get the value of bending moment. Let me know the value of moment. What is the value? 56.25. Okay. This is 56.25 kilonewton meter. This is the moment. Okay. So now this is the moment. Then we will calculate horizontal shear force. Horizontal shear force. Okay. So what is that horizontal shear force? S. Horizontal shear force. This S is equal to. See, again I will tell you how that force is there. This diagram, again there is no need to draw. Here it is our section. Okay. This is point PP over here. Okay. Now this is 400 mm. This is 300 mm. And over this entire area, the intensity of the stress is 3.125 MPa. This is the stress over this entire area. Now I want to calculate the force. Okay. So the basic formula for the force is stress into area. The basic formula for the force is stress into area. So stress is 3.125 into what is my area? It will be 400 into 300. If 400 and 300 kutna ala? So I am talking about this. Here I will tell you. I am talking about this much of thing. This much means this area. This P point up to this above section. This much. I am talking about this point. Okay, about this point. This horizontal is 400. This vertical is 300. And on this area, you can see here the intensity. Intensity is this much. This is 3.125. Okay. So that is what we are doing for the calculation. We're taking for the calculation. So this is the yes. So if you calculate the value of yes, then let me know the answer. If you calculate the value of this, then let me know the answer. 3.125 into 400 into 200. What is the answer? 375 kilonewton. Okay. So it is 375 kilonewton. This is the answer. Now vertical stress. Now we will calculate the vertical stress. So vertical stress E of Z is equal to, the formula is Kz into M upon Vd square. So therefore Fz is equal to Kz, the value of Kz, it is given in the numerical itself, I think. This constant values. Yes, Kz is minus 5. So Kz, I will put this value as minus 5 into moment, it is 56.25. So it is 56.25 into 10 to the power 6 divided by Bd square. So B is 400 and D is 800 square. If you solve this, you will get the value of Fz. Let me know the answer. What is the answer? लेक्चर चालू आहे माझं अर्जंट आहे का so what is the value of fz if you put all the values minus 1.09 okay so it is minus 1.09 MPa this is your vertical stress okay this is your vertical stress now we will calculate the shear stress now further we will calculate the shear stress so shear stress Q is equal to it is KQ is KQ into S upon BD. It's KQ into S upon BD which is equal to okay put the values and let me know the answer. What is the answer? KQ value is 1.25 into this yes we have calculated 375 into 10 to the power 3 kilonewton to Newton. B is 400. D is 800. Let me know the answer. 1.46. Okay, so it is 1.46 Newton per mm square. 1.46 Newton per mm square. Now we will calculate the principal tensile stress. Okay, so in the numerical, what they have asked us further, see, find also, here it they have told us, find also the principal tensile stress at the above section. Principal tensile stress they have asked us, not the compressive stress they have asked. So principal tensile stress means minus sign we need to use. Okay. So principal tensile stress they have asked us. So next, principal tensile stress sigma t is equal to fx plus fz divided by 2 minus under root here fx minus fz by 2 whole square plus q square. So put the values and solve this. Sigma t is equal to what is the value of fx? 3.125. Okay. So minus so plus what is the value of fz? Minus 1.09 divided by 2. Again minus in under root square root fx 3.125 minus minus will become plus. Okay, so minus of minus 1.09 divided by 2 whole square plus 1.46 square. So therefore, sigma t is equal to what is the answer? 2.6. Check the answer once again. I have solved this. I have got the answer minus 1.55. Okay, correct. 1.54 minus 1.54 is the correct answer. I have got minus 1.55. So minus 1.54 MPa. This is the correct answer. Okay. This is the correct answer. So now moving further, this is for second. This is given in the, see here at the edge. This is second thing which is asked. Now we will go for the first thing. What is asked in the problem? First, they have asked us through center. Through center. Okay, that is section Q2. Through section means center means section Q2. Now we need to think about this Q2. Okay, so the momentum will be, if I calculate the moment, it will be 3.125 into 400 into, again it is WL square by 2, 400 square by 2. Okay, here you can see now. Now see here, now we are considering from this point here. So this horizontal distance is 400, we know that. But this vertical distance now, this vertical distance will also 200 plus 200, 400. So this whole square now we are considering, it is 400 by 400. So here also now the pre-stressing force which is acting at the here at this point, this also we need to consider. Pre-stressing force which is acting over here. Okay, this also we need to consider, and this pre-stressing force is 1000 kilonewton. But what we generally assume that whenever there is a single anchor plate is there, then we take always average pre-stressing force. We assume that the pre-stressing force is acting over here, but it is acting everywhere on this anchor plate. We are acting everywhere on this anchor plate. Okay, so we consider that from the centroid, what is this centroid line? For above portion, half of the pre-stressing force is there. For below portion of this centroid up to the anchor plate, half of the pre-stressing force is there. Now this section which is here at this point, so for this topmost half portion, we will consider the average pre-stressing force, and that average pre-stressing force we should consider here, it is P by 2. Okay, so P by 2 means 500 kilonewton is the pre-stressing force that we should consider over here. And for the moment up to the edge, the distance is 100 mm. So we will consider this also in the our calculation up for this point up to here, up to this point. Okay, so now if I take it into the consideration, then here it is minus 1000 into 10 to the power 3 divided by 2 by doing the average into 200 by 2. Okay, so now if you solve this, what is the value? M. What is the answer for the moment? M is equal to, calculate this. It is 50 kilonewton meter. It is 50 kilonewton meter. Okay, 50 kilonewton meter. So you know the shear stress distribution. Shear stress is at center, your horizontal shear is 0. Okay, at center your value of S, it is 0. Therefore Q is equal to 0. Okay, so in the formula of Q, S is there, so it is 0. Now the vertical stress that is Fz, which is equal to Kz into M upon BD square. So Kz is minus 5 into M. M is 50 into 10 raised to 6 divided by BD square is 400 into 800 square. So therefore, Fz is equal to, calculate it, Fz minus 0.97. So minus 0.97 Newton per mm square. Okay. So now further we calculate the principal stress.
सर
हा
ते ह्याच्यामध्ये व्हर्टिकल स्ट्रेसेस काढताना D400 घ्यायला पाहिजे ना?
ही काय घ्यायला पाहिजे?
400.
No. Why to take 400? It is the formula which is Kz here. You can see here. Fz is equal to Kz upon M upon BD square. This formula is derived now. In this formula here, there is no term like dV or anything else for the vertical stresses. Vertical stress distribution, it is vertically stresses are there. So here we are going to consider the depth as it is. We are saying that you are mixing this formula with this. Here for the horizontal stresses, we take it in that way. dV is the depth. Okay, for the horizontal stresses, and that too when the point where we are calculating that horizontal stress that comes into that dispersion, then only our depth get varies. Instead of d we go for dv. Okay, if you look at the formula here also while calculating the shear stress, this d is the formula, d is the depth. Okay, here also fz kz m upon bd square, here d is the depth, it is not dv. In the formula of fz also d is the depth, and in the formula of q also it is d is the depth. The derivation of this formula is, it is not there for your syllabus. Okay, this also here now dv, here it is not the depth, here it may come d or it may not be d. Okay, depending upon the section where that point is situated. It is for the horizontal stresses. Now for the shear stresses and for this vertical stresses, it is d. Okay, in the formula itself it is d, so there is no question of changing the depth. Okay, so now here m upon bd square, here it is again, I am saying that, repeating, here it is not dv. dv is only in for the horizontal stresses, it is not for the vertical stresses. So for the horizontal stresses you should consider that, don't consider it for the vertical stresses. Okay, so now fz is equal to, here it is kz upon kz into m upon bd square. So the value of kz is minus 5, value of moment it is 50, and now bd square, so 400 into 800 square. So by using this, we will get the value of fz, and fz it is minus 0.97. Okay, my value is also near about same, minus 0.97. I have calculated minus 0.96. Okay. So now principal tensile stress. Principal tensile stress, and this is again sigma t. Again we will use that formula, fx plus fz divided by 2 minus, here in the bracket fx minus or plus minus, okay, minus fz by 2 whole square plus q square. Okay, so if you put the values, therefore sigma t is equal to fx 3.125, fz plus here minus 0.97 by 2 minus here in the under root 3.125 minus of 0.97 by 2 whole bracket square plus q is 0 square. So put all the values and let me know the answer. So sigma t final value which I have calculated, I think it is 0.97 plus. Calculate it. What is the answer? Minus 0.97. Okay, so sigma t is minus 0.97 MPa. Okay, so this is the value of sigma t, principal stress. So we have calculated the principal stress, whatever they have asked us in the numerical. If you see the numerical, they have asked us that calculate horizontal, vertical, and shear stress. This we have calculated, and the principal stress at above section, and also the principal stress we have calculated in this unit. So this is the one type of, only this type of problem which can be asked on the Magnus method. Okay, so go through this problem. Let's see the problem after the lecture. Also go through this problem, see the problem, what is done in the numerical, how it is done, how it is calculated. Your concepts of the shear force bending moment must be perfect. You learn this in the second year. So again, if some confusion is there, go back, see the concept, and then try to apply over here. Okay, so bending moment calculation, now you should be in a position that you can directly do the write the bending moment equation. Likewise, whatever I am writing over there, okay, directly, likewise you should be perfect in that. Okay, so it is required. Okay, it is very much required. So now this is the only single type of problem we have solved. So if possible in the evening also I will take the lecture at 2:45. Okay, at 2:30 I will share the link with you if I don't have any other emergency work. In evening session is your gate session now today. If possible, then I will take the lecture, and in that lecture we will see the Guyon's method now. Okay, so today for this lecture now we will stop over here. So I will take the screenshot for the attendance. You wait. I will take the screenshot. So today I think 11th December. 11th. Okay, now you can drop your roll number into the chat box and you can leave the lecture.